welcome back from spring break. I hope you actually all got a break and are back and rejuvenated and relaxed. I'm sorry about the rain, but we tried to optimize for it. Didn't really work. Anyway, today you have a special treat. Many of you probably already know Sylvia. She's going to be giving a guest lecture on linear programs, since a lot of her work deals heavily with optimization. She works actually on understanding the limits of safety in the sense of control systems, when thinking about how you develop algorithms that guarantee that, let's say, a UAV is safe. So if you have questions about that, I'm sure she'd be happy to answer during office hours. So just a quick reminder that next week will be a midterm. There'll be a review session Friday night. Location will be posted to Piazza. So don't forget to show up for the midterm. And with that, I will give it to Sylvia.
Thank you. Hi, everyone. Oh, you don't need to do that. Thanks. My name is Sylvia. I'm a fifth-year PhD student here in EECS, and I work for Professor Claire Tomlin, who actually is Professor Bayan's PhD advisor as well. So Professor Bayan and I are what's called like academic siblings. And as Professor Renate mentioned, I work in safety and control systems and robotics. And what's nice about it is the math is very, very general. So it can be applied to a UAV, making sure that that stays safe. It can also be applied to, giving someone anesthesia and trying to make sure that you keep them under without having them enter the unsafe states, where unsafe states here is death. So it's a really fun topic. If anybody wants to talk about that, I'll be at office hours right after this. So including any questions as a lecture, questions on research, or questions on grad school in general, I'm happy to talk about those. All right, so the next few lectures, we're going to be starting to talk about different types of optimization problems. And one might wonder why we care so much about these different general forms for optimization problems. And it's because when you have problems in a set form, you know what type of algorithm is required to solve that problem and the complexity of that problem. And so a lot of what's tricky about optimization is taking some confusing mass of qualifications that somebody at some industrial plant might ask you to optimize for and turning that in to an optimization problem of a standardized form that you can plug straight into an algorithm. And moreover, you don't want to just find any old form. You want to find the cheapest possible form, so the form that has the cheapest algorithm associated with it. If that makes sense. So we're going to start the lecture, or this series, so this lecture, with kind of the simplest form when you go beyond least squares, and that's linear programs, which you've seen a little bit already in the class, but we're going to go more into detail of that. So we're going to be discussing, what are linear programs, or LPs? Can we turn problems that don't look like linear programs into linear programs? And then some examples on that. Are there any questions, just high level, on any of what I just said? Okay, great. Let's start off with a little bit of history. So first off, we have our friend Fourier, which we all probably are familiar with. So Fourier was the scientific advisor to Napoleon Bonaparte and accompanied him on his expeditions to Egypt and got really interested in, Egyptian artifacts and whatnot, and also into, his main interest was in heat transfer and how, when you take a sword and you're forging it, the heat goes throughout the sword so you can best hammer it and whatnot. And so he's really famous for his work on heat, but he also was the first person to solve a system of linear inequalities in 1827. And then we can fast forward to World War I, and we have Kantorovich from the Soviet Union, who was trying to figure out how to maximize losses on the enemy, subject to constraints like military constraints and soldiers and whatnot. And he was the very first person to actually formulate the linear program formulation. And he and this other Dutch scientist who continued to work on that ended up winning the Nobel Prize in economics for this. And you'll kind of get a sense for why this is so important in economics once we get to the famous Professor Bayan winemaking problem. But this was a really big deal at the time because optimization is so powerful. So that's our little bit of history. And now let's talk about what a linear program would be. So let's just start simple. We're going to minimize some objective function, where I'm just going to make this objective function cx plus d. So x here is a scalar. So scalar x, no constraints, just cx plus d. So if you look at this, this should immediately start ringing your, it's a line bell in your head. This is an affine function. This is a linear combination with this offset affine term. And if we look at what that will look like, on a graph, we plot our domain x, which in this case is all of R, and then we plot our function. So if I'm set, c equal to -2 and d equal to 3, then, our intercept's going to be 3, our slope's going to be 3, our slope's going to be -2, and our function will look something like this. So here, if we think about trying to minimize this function, it's fairly obvious. You see as x increases, the function goes negative, and so we're kind of sliding down this slope in order to get to the point where x star, in this case, equals infinity, so that p star equals -infinity. But more generally, when we have this general form, how do we choose x? Does x depend at all on this d term? No, there's no x associated with this d. So solving the optimal value for cx plus d and solving the optimal value for just cx is going to be the same process. That's why even though this is technically affine, not linear, we're still doing essentially the same exact thing as if this was strictly linear. So we allow affine objectives to be considered linear in the sense of linear programming. Now, how is x related to c? Well, if c is positive, then we're going to choose x to be as negative as possible, so that when we multiply something negative times something positive, we get something big and negative. So in this case, when it's unconstrained, we'll choose x to be -infinity. And when c is negative, we'll do the opposite, right? We'll try to amplify that negativeness by making x as positive as possible. So you'll see that we take c, and we're choosing x to be as strong as possible in the reverse direction of c. So we're moving along -c here. Now, what happens when c is 0? Well, just by inspection here, when we plug in 0 here, we get f naught of x is equal to d. So x can do nothing, really, in this situation. Your minimum value is going to be stuck at d forever. Okay, so now if we just added some sort of constraint, so let's just add right in here such that, x is less than or equal to 5. Or here's 5. We're still going to try to move as far as possible in the direction of -c, but we're going to be stuck at the particular boundary of the constraint. Yeah, pretty straightforward. All right, so let's go ahead and move beyond scalars. So now I'm going to do minimize c transpose d, x plus d, where now we'll just put x in R2 because I can still draw in 2D. C I'll set as 1, -1, and 3. And D I'll keep as 3. Okay, so here our domain is going to be R2. So it's just like over here where our domain was R, we had a 1D domain and we plotted over that 1D domain. Now we have a 2D domain and we're going to plot over that 2D domain. I'm very bad at drawing 3D, so instead we're going to look at some pretty MATLAB figures. All right. So again, here's my x1 and my x2, and my domain is going to be this gray area. It's going to be everything. I'm plotting -5 to 5, but you know what I mean. It's going to be all of this. And now really try to think of that as like the horizontal surface that we'll be plotting over. So I'm actually going to go ahead and just rotate this. And so we have our domain, and we're going to be plotting our function over this domain. And now I'm going to plot this function, which is, again, just the c transpose x plus d. And it looks something like this. So if I rotate it around a little bit, that's kind of what my function looks like. Where it's this plane over our domain. And we see that as we get more negative, so in the areas of darker blue, we can push ourselves towards more negative values of f, right? So let's see about what we'll be doing there. So you see x1 to get to more negative values is going to be becoming more and more positive, and x2 is going to be becoming more and more negative. Does that align with our tuition from the scalar case? Well, the first component of c is negative, So x is pushing in the positive direction. Second component of c is positive, x is pushing in the negative direction in order to get to more and more negative values. Does that make sense? Okay, so in optimization, as we talked about before, it's tricky to draw these types of things, so we really like drawing level sets of functions, where really you should just think of level sets as contour lines. So I'm just calling contour on this function, and these are all lines of equal value along this function. So you see that there are different colors here, where, a line of a particular color is equal to where that function is set to a specific value. Let's remember what these level sets are like. So my contour for some particular value, let's say a, will be the set of states such that when I plug those states into f, they will all equal the same value a, or alpha, here. All right. In general, these level sets are going to be orthogonal to the gradient of the function. Now, this is true in general beyond just our linear functions, but this is particularly true for here. And it's useful to remember this, and let's think about why that is. Well, first, let's talk about what the gradient of our function is. So the gradient of f naught of x equal, what's the gradient of this function with respect to x? Can someone say it slightly louder? C. Great. It's C. Okay, so C should be orthogonal to these level sets. I'm going to redefine what these level sets are by saying, okay, I'm going to try to draw this. Here's my x1 and my x2. Here's like some function over that. And then let's take some point x naught. Let's plug that into our function. It's going to give us something here. So this is going to be f naught of x naught. And I'm going to choose that to be equal to my alpha. Now if I plot the level set here, I'm going to define it as taking this x naught and adding some sort of vector v to it. I know this is kind of hard to see. Let me plot it a little bit bigger. My f of x naught. And here's some vector v that goes along the line of this level set. Then I'm going to rewrite this as my set of vectors v such that when I find f of x naught plus v, that's going to be equal to f of x naught, which is equal to my alpha. Right? So again, this is just saying when I add any component of this vector and I plug that into my function, it's going to still be the same value. So we're staying along that same level of value. So why would this be orthogonal? Well, let's look at the Taylor's expansion around that point. F of x naught plus v will be equal to f of x naught plus how far I move along in the v direction. So my gradient of f times x naught plus v minus x naught, which is going to be v, so times v. So this is going to be equal to f of x naught plus c transpose v. Now, from my definition up here, I know that if they're on the same level set, then f of x naught plus v is equal to f of x naught. Right? So I'm going to go ahead and plug in f of x naught here. So we see that these cancel out, and we end up with 0 equals c transpose v. So 0 equals our gradient c, transposed or inner producted with any vector along these lines of continuous value. So this is all a bunch of stuff to say, just kind of what might be intuitive, which is if I take these level set lines and now I rotate back and just look at my level curves over my domain, I can see how they move or how they are aligned by looking at the gradient c. So just think about this here. C is minus 1, 3, and work out in your head if that makes sense what the arrow is doing. It's moving in minus 1 and up 3. So this is useful because now if we have our domain and we know what the level sets look like, we know that if we move in the direction of C, we're going to be moving up the gradient. We're going to be doing gradient ascent and moving to higher and higher values of f, right? However, in minimization problems, we typically want to do gradient descent. And so, again, we want to move in directions of minus c. So this ties us back to our very first scalar case, where, again, we're just moving along directions of minus c. Are there any questions at this point? I'm sorry, can you say that again? Oh, you can think of x naught as a vector as well here. Does that help?
I was thinking the v should, instead of v, should be x naught plus in
The set of...
second line.
Oh, I see what you're saying. For the set of states, you're saying just do x naught plus v. Sure, yeah, you could write that in. Here, let me... You're saying x naught plus v here. Okay. Are there any other questions? Okay, great. Okay, so in this case, our optimal point will be if we move x1 in the direction of infinity and we move x2 in the direction of minus infinity. Now, what happens when we have constraints? So moving this aside, let's give ourselves some constraint. Let's just start with saying that x needs to be in between some min and some max value, or I'm going to set that as just between minus 2 and 2 in each direction. This will result in us having a square. So now our domain is restricted to this square, and we need to to be able to find the minimum value here. Here's our square. And we have, these level sets that are moving in the direction of minus c. And the nice thing about thinking about these level sets methods is that we can just continue to slide down levels of minus c until we get to the point where we're barely intersecting with our domain. And this will be as far as possible as we can move in our domain in the direction that we care about. And so in this case, it will be on this particular vertex where x is still as positive as it can be, so 5, or 2 in this case, and x2 is as negative as it can be, minus 2 in this case. And we end up with our minimum value being at this particular vertex. So for an LP problem, our constraints must also always be affine. So they don't necessarily have to be square like this, where each x is independent. They could depend on each other. But they always must be affine, which means that we're always going to have this intersection of different halves of hyperplanes, and we'll have a polyhedron for our domain. So thinking about it now, again, think about moving down those level curves until you get to the tip of what's correct, and ask, will there ever be a case in which our optimal value or our optimal point will not be on a vertex? So for the polling, this is what they do in some of the psychology classes I take. You hum instead of raise your hand. So that way you don't have to reveal yourself to having opinions. So, and we judge what people think about based on the volume of the hum. So people who believe that that there can be an optimal point that's not at a vertex, please hum. Okay. People who believe that the optimal point will always be at a vertex, please hum. Okay, all right. So we got a little bit in between. And I think the answer is a little bit in between. So let's look at, for example, this particular one, where we have this domain where we have an entire edge that aligns along our minimum level set. So here, there are points that will give us the minimum value that are not on the vertex. But at least one of these will always be a vertex, right? And so this problem of linear programming comes down to finding efficient ways of picking out the best vertex that will give you your minimum value. And so you can imagine thinking algorithmically why this might be useful and why it would be nice to be able to formulate things into a linear program, right? Okay. So let's talk about the general form of an LP. So we want to minimize our C transpose X plus D subject to our inequalities, that must be affine, and our equality constraints. So we have an affine objective function and affine constraints. So I know it's a little bit weird saying that a linear program has affine ones of these, but just remember that. Okay, let's do an example. And let's do our example that we've been doing in this class, winemaking. So again, we're trying to figure out if Professor Bayan should quit his job and go make wine instead. Here's our setup. Professor Bayan has 2,000 kilograms of Merlot grapes and 1,500 kilograms of Shiraz grapes. Here are the wine blends he can make. So we have blends 1, 2, and 3, and they require this amount of Merlot grapes and this amount of Shiraz grapes, and this is the amount of profit that he can make. So if he sells them, this is how much he makes. And the goal here is to maximize his profit, subject to the constraints that he can't produce negative bottles, and he can't use more grapes than he has. You can see how you could formulate many, many economic problems in terms of supply chain management and whatnot into this sort of form. And we want to transfer this into our standard linear program form so we can actually plug it into one of our algorithms. Let's talk about how we would do that. So maximize profit would mean I want to maximize the amount of profit I will make off of blend 1. So $20 of blend 1, which we'll call Q1, plus the amount that we'll make off of producing the second blend, plus the amount that we'll make off of producing, that was 25, the final blend. So this will be our profit, and it's subject to the number of bottles we make of each one of these must not be negative. This is a constraint that's often frustrating in engineering when you have negative, or when you have things that can't go negative. We also have that we can't use up more Merlot and Shiraz grapes than we have. So we would make, for each Q1, we'll use up 10 Merlot grapes. For each Q2, it'll be 8. For each Q3, it'll be 7. So all of these grapes must be less than or equal to 2,000. And then the same thing for Shiraz. Okay, so let's turn this into our general form. So we want it to look like minimize C transpose X, where here we don't have a plus D, subject to, and here we just have inequality constraints. First question, here we're maximizing profit, and we want to turn it into minimizing something. How can we do that? Is it possible to do that? You're nodding. Do you have any feelings on how we could do that?
On our homework, you just added negative to the objective function.
Yeah, so affine objectives are nice in that they are both convex and concave. And we know that if we maximize a concave function, we can flip that and minimize a convex function, right? And so since it's both convex and concave, we can turn our maximize profit into minimize negative profit. And so we should expect a negative answer out of this. So to get negative profit, we'll set off C equal to minus each of these, so 20, 15, 25. We'll set our x equal to Q1, Q2, Q3. And then our constraints. So we'll have some Q1, Q2, Q3 times some G minus some H. For here we have that Q1 can't be less than 0, so we'll have for Q1 that. Then our same constraint for Q2, same constraint for Q3. And then we plug in our other constraints here. So 10, Q1, 8, Q2, 7, Q3, 5, 4, and 15. And then these have to be less than 2,000 and 1,500. So this will be our G, and this will be our H. Now we have this in our standard linear program form. And here I'll just go ahead and plug it into CVX here. So here I'm saying our x has 3 dimensions. Here's my G. I'm just copying it down. Here's my H. Here's my C. I'm going to do CVX begin of C transpose X subject to Gx minus H is less than or equal to 0. Let's go ahead and run this. And we end up seeing that our optimal value is going to be negative 4,478. When I first plugged this in, I was like, wait a second, negative, what does that mean? We're trying to do profit. I had to remember, again, we're doing minimizing the negative profit. So it makes sense that we're getting a negative value out of this. And as for our optimal point, he should make this many of each of his types of blends. So we can give this to Professor Byen and say, hey, you can make, over $4,000 on your winemaking business. Are you ready to quit being a professor? See what he says. He's not here today. I was hoping he'd be here so we could get an answer on that. But okay, all right, so that's the general formula for a linear program. Are there any questions about just generally what a linear program looks like and how we would take something that looks linear and put it into the linear program formulation?
Can you just go over the dimensions of G? Because I can make the last, like 10, 8, 7, 5, 4, 15.
Yeah, sure. So the first 3 are just doing this version where we the first 3 constraints up here where we just want, Q1 is greater than or equal to 0, but we need this in terms of a less than 0 form. So we want, minus Q1 is less than or equal to 0. And so we have Q1, so minus 1 of Q1, 0 of Q2, 0 of Q3, minus 0 is less than or equal to 0. Any other questions? Okay, so linear programs are nice. It would be great if we could solve everything using linear programs. Unfortunately, that's not always the case. And so a big thing in optimization is can you come up with these clever tricks for taking something that looks a lot more complicated than it truly is and converting it into something that's simple? And it's this beautiful art form. And when you see some of these grad students that know how to do this, it's just astounding. They just have this intuition inside of them where they just can look at something and immediately. But it doesn't come immediately. It's a lot of practice. And there are many interesting tricks that one can do. But we're going to be talking about one of the most common and most useful, and that's probably useful to like store in the memory bank and or a future cheat sheet, and that will be the epigraph trick. So, does this have an official name? I've been calling it the epigraph trick. I don't know if there's like I'm sure that there's some like old scientist who put their name on this, but this is what I call it. Okay, so first, in order to do the epigraph trick, let's go ahead and refresh ourselves on what epigraphs are. So I'm going to have some function I want to minimize. I'm just going to make it equal to absolute value of x here, where it's scalar. And I'm going to just say subject to x has to be in between -1 and 1. So x is scalar. I'm plotting the function over this. Absolute value of x looks something like this, except I'm stuck between -1 and 1. So really it's like this. And this is my... So this is not linear. I mean, this looks kind of linear, like you have some straight edges, but this is not a line. You cannot represent this using cx plus d, right? Now, let's talk about what the epigraph of this is. So an epigraph is when we take a function and we turn that function into a further set. So we're taking this function where we have this 1D domain, and then we're plotting the function over this 1D domain, and instead we're going to turn it into a set that looks like this, where my epigraph of f naught is going to be taking my x and adding a dimension t. So now it's going to be r of n plus 1, or in this case, r of 1 plus 1. And it's restricted to, so x still needs to hold the same properties that it held before. So it still needs to be in the domain of f naught, whatever that meant. But also, our new dimension t must be greater than or equal to our function value. So here's a particular, so here's t, x and t now, instead of x and the function. And here's a particular point, xt, that works. So x here is in the domain between -1 and 1, and t is in the domain as well, because it's greater than f naught. So let's go back to plotting things in 3D so I don't have to try to draw them. Come on. My computer is frozen. Is it frozen? No, it's not frozen. Oh, it's now connecting. Oh, jeez. There we go. Okay. Okay, so there's my absolute value of x. And here's my epigraph. So again, the set of points xt, where here's a particular xt, such that x is in the domain and t is greater than our objective function. Now, please remember that this is now our new domain. So think of this now as that horizontal surface, the domain over which you're going to be plotting your function. Okay? So the epigraph is a set and is now our new domain. So here's our domain, and we know what this domain should describe, right? So we have our subject to ready, where we have the same constraints that x must be between -1 and 1, but also now that t must be greater than or equal to our objective function, the absolute value of x. Now, what is our new objective function that we should solve over this domain? Well, if you look at this and think about what we did before for our linear programs, we really want lines or level sets that will move in the direction of -t, right? Because we want to push this down as far as possible until we get to the point where we barely intersect with the set in order to find the minimum value here. And so since we want to move in the direction of minus t, we should set our new objective function equal to t. So in the same way that you might set y equal to x and you get a straight line, we're going to go ahead and set our new objective function equal to t. Does this make sense? If this doesn't make sense and you prefer thinking about epigraphs purely abstractly, go for it. Don't worry about it. But if you prefer thinking about things graphically or visually, this might help a bit. Okay, so now we have minimize t, subject to the absolute value of x is less than t, and x must be between minus 1 and 1. Now, is this a linear program? Do we have an affine objective function? Okay. Do we have affine constraints? No, at least not yet, because we have this absolute value here, which is not like a linear function. However, now that we're looking at constraints, we know what an absolute value looks like, right? We know that absolute value means that x has to be less than t, or x has to be greater than negative t. And so we can turn this one constraint with an absolute value into two constraints. People following this? If there are any questions, this is the time to ask them. Yeah. In the same way that I split up the x between minus 1 and 1, I'm splitting up the absolute value of x into x is less than or equal to t, and x is greater than or equal to minus t. So these are all affine now, which is great. But we need to, if we want to be legit, we should convert them into proper form. So I'm going to move everything over to the left-hand side so we get everything less than or equal to 0. And then doing the same thing that we did with Professor Byon's winemaking problem, we can convert this into our gx minus h is less than or equal to 0. So now, do we have an affine objective? Yes, t is just t. Do we have affine constraints? Yes. We just have a series of affine constraints. And so we're able to turn this function that is not linear into a linear programming problem. So how are we able to do that? In what cases can we use this epigraph trick? Take a minute to think about that yourself while I prep. Any thoughts? Oh, sure. Mm-hmm. Yeah, so I can go over that again. Did this part make sense where we would like to be able to have level sets that move in the negative t direction? Because we want to minimize, we want to find the x star t star that will minimize this function, right? And in this particular case, we can see by inspection that it will be down here. In general, we can change this into a linear programming problem by looking for a function that will move in the direction of minus t here. And so we want some function that will allow us to do that. And the function is simply going to be f naught of x equal to t. So if you think about level sets of this function, I didn't plot the level sets, I probably should have. Level sets of this function will be lines that look just like the lines that I drew there. And we can solve in the same way that we've been solving our linear programming problems. If the graphical representation is weird to you, don't worry about it. Just remember the epigraph trick, which we'll go over the general form in just a second. Yeah, we're actually going to be doing several examples using the epigraph trick. So why don't we go through those, and if there's still a question, then we can come back to that. Does that make sense? Okay, so does anybody have any thoughts on when this epigraph trick would work? If x is the max of linear functions. So yeah, that makes sense. We can change this absolute value into the max between minus x and x. And here we have a max of linear functions. So yeah, that's a case in which this works. Are there any other thoughts on when this works? It needs to be convex. Yes, absolutely. So if the absolute value there wasn't convex, then when we turn this function into a set, we would end up with a set that is not convex. And for any convex optimization problem, the domain over which you're solving needs to be convex, right? So that's absolutely a requirement. The epigraph is a polyhedron. Very nice. So that's saying that even if the function itself isn't linear, when we look at the epigraph of that function, it must satisfy our requirements for the domain of a linear program, where the requirement was that the domain is a polyhedron. So we need our functions to be such that their epigraphs are polyhedrons. So let's write this down. We need constraints to form a polyhedron. So this is just generally what we need for a linear polyhedron, a linear programming problem. And so we need our function to be such that the epigraph will do that. And those types of functions are called polyhedral. So polyhedral functions are functions whose epigraphs are polyhedrons. So the general thing you should be asking yourselves is if you look at an objective function and it only has affine constraints under it, say, if I were to move this objective function to the constraints using this epigraph form, would I be able to convert it into a set of affine constraints that will allow the constraints to be a polyhedron? Here, I'll do it over here. Okay, so the general form for this will be if we have min over x of f naught of x subject to some ax is less than or equal to b, we're going to instead say minimize over t. We're now, your domain is x and t, subject to ax is less than or equal to b, and all of our points are inside of the epigraph of f naught. So this is all affine except for this part, potentially. So we need to make sure this is affine. Okay, so let's do a few examples to get more comfortable with this. So, example. We'll do piecewise linear minimization. So we want to minimize our objective function. Where our objective function here is going to be exactly what you said, the max of several affine functions. So this is saying, I have some domain, and I think we have m, ai, x plus b. So several different lines in this domain. And we're taking the piecewise maximum of them. So if I look at the max between all these, it'll, be something like this. Yeah. So we can start by asking, what we said, is this convex? In this case, yes, it is convex. Is it linear, though? Is it affine? And no, it's not affine. This cannot be represented by the line, for an equation for a line. Yes? Oh, yeah, sure, I'm sorry. Hey, let's do it over here larger so we get a sense for that. Thanks for asking these clarifying questions. It's good to make sure that we're all on the same page. So here's a particular AI transpose x plus b, right? Where here we have the slope and here we have the intercept, bi. And we're going to have several of these lines. So let me draw a line like this, and maybe a line like this, and I don't know, one like this, and like this. So we have m of these lines. And we want to say that our objective function is to take our x, plug it into each one of these lines, and then choose the maximum value of that, right? So if I would take, x is 5, for example, I would plug that into this guy, and this guy, and this guy, and this guy, and this one, and I would choose the max of all those, so here. And if we sweep out doing that for every single point here, we're going to end up always taking the top value that we have here, right, the maximum. And so let me do this with another color so it's a little more straightforward. So over here, the maximum is going to be at this line. Between here and here, the maximum is going to be at this particular line. And between here onward, the max is going to look something like that. So I didn't draw it exactly the same, but it's the same idea. Does it make sense? Okay, great. Let me erase this then. Okay, so let's do our epigraph trick. I guess I'll keep this here for now. So now we're going to instead minimize t, xt, and then we're going to throw our objective function into the constraints. Subject to max I equals 1 m of ai suppose x plus b is less than or equal to t for all of our, or no, that's just how it is. Okay, so we have minimize t subject to our constraints, so subject to our maximization. Again, this is still not linear. So when we just take something that doesn't look linear and throw it in the constraints, we didn't magically do anything. It still doesn't look linear. So we need to do a little bit of math to figure out if we can turn this into something that does look linear. Okay. So we have our max. And now, this particular constraint, when we look back at our graph, we're saying that we want this green curve to be less than or equal to t. So t is always going to be above here. And now, if you think about it, this is equivalent to saying that this must hold for this particular line, and this particular line, and this line, and this line, right? For every single line here, t must be greater than or equal to that line. So I can turn this into saying that ai transpose x plus bi, every single one of these lines must be less than or equal to t. So for every single one, so for all of my I equals 1 through m. Does that make sense? So I've taken my constraint, this one constraint that does not look linear, and I can convert it into a set of linear constraints. So now I have m linear constraints instead. A polyhedron is a set of the intersection between a bunch of linear constraints here. So you have, this t must be greater than or equal to this line. T must be greater than or equal to this line, et cetera. And when we take the intersection of that, that will be a polyhedron. Okay, some other polyhedral functions. Let's do this one. One particularly useful one is the one norm. So the one norm is equal to the sum of absolute values of xi, right? And so we can actually write this as the sum of a set of maximizations of affine functions. And since we just did maximization of affine functions, this should start ringing a bell. This is useful because we often like to do L1 regression. Where we're going to do minimize the norm of AX minus B. So we have some X, we passed it through A, and we ended up getting measurements B, and we want to find out what that X must have been. So let's say, we pass a scene through a camera, we end up with some measurements, and we want to figure out what that scene must have been, given that. Oh, sure. This is, I don't have it written up anywhere, but when we did absolute value of X, so this was absolute value of X, when we turn this into constraints, or we could write this as taking, this line of minus X and this line of X and taking the maximum between them, right? In the same exact way that we did here. We're taking the max here between X and minus X, which is this, and the max here between X and minus X, which will be this. Thanks again for asking questions. Okay. So we wrote out our L1 regression problem, where here, A is going to be our standard n by n, and B. Okay, so this now can be turned into minimize X, and I'm going to plug this in, a sum from I equals 1 through n of my absolute value of AX minus B. Or sorry, for each one of these, AI transpose X plus BI. So this is just rewriting this norm. And now again, we're going to have now a sum of the absolute value of a function. So we're taking a sum of polyhedral functions. And so I can turn each one of these polyhedral functions into my own little epigraph. So I'll write this as minimize over xt, a sum now. Note that this is slightly different, of ti's subject to, and now I bring the objective functions down, ai transpose x plus bi, absolute value of that is less than or equal to t for every single one of my i's. So this is very similar to this step that we took here. And now I'll just keep going down here. So this is the same. Because remember, this isn't quite in our LP form yet. So this is the same as saying taking my C as just a vector of 1s transposed with T, where here I'm just stacking all the Ti's, subject to. Now I'm going to turn this absolute value into two constraints, the exact same way that I've been turning the absolute values into two constraints. So just AI transpose X minus BI, this minus is less than or equal to T, and then also AI transpose X minus BI is greater than or equal to negative T. So now we have an affine objective function and affine constraints. So we've managed to turn our L1 regression problem, in which we had this norm that we had to deal with, into a linear program. I wonder if professors have super strong right arms. So I've been doing this. My right arm is really sore now. It's probably more of a comment on how many more pull-ups I should be doing. Okay. So another one that is nice is the infinity norm. So here, if we have some function that is our infinity norm, if you recall, our infinity norm is taking the max of our absolute value of xi's. And so, again, it's an absolute value. So we can say that this is the max of the max between let me write this down here. Equals between xi and minus xi. Same exact logic as we did before with the max. And so we have enough time, I think, for L infinity regression. We want to take the minimum now over x of ax minus b again, but now with respect to the infinity norm. So I care about the maximum values of x. And I'm going to go ahead and turn this into our epigraph trick. So minimize x of t subject to my norm. Where I know that ax minus b, the infinity norm of that, is going to be the max of the absolute values of those. Just plugging in infinity more. And then I'm going to say that that's going to be less than or equal to t, which, using, again, very similar logic, we're saying that the maximize of that, I erased it. The maximize of a bunch of different lines is going to be equal to setting the same constraints for every single line. So just removing the max and saying that ai transpose x minus bi must be less than or equal to t for every single one of these i's. And then, again, change that absolute value. And then ai transpose x minus b I t. And both of these. So again, now we have our minimum of t subject to these constraints. So we have our affine objective function, affine constraints. We're able to turn L infinity regression problem into a linear program. Okay, so I think we have time for one last fun problem. Oh. Yeah. Yes. Thank you. with respect to x and t. Oh, sorry. Thank you for that. So minimize over x and t. Okay. So I think of this problem as fun. This is a Boyd problem. And it's on finding the Chebyshev center of a polyhedron, which sounds super abstract and something that just like people who want to sit around doing math all day would do. But I promise it has real applications. So Chebyshev center. Okay, so say you own a business and you're manufacturing something, some part, some like mechanical part, and you have some constraints that part must satisfy. So you know that the part must, satisfy a series of constraints and parameters, and you end up drawing a bunch of affine constraints, and you end up with a polyhedron that is the set of admissible parameters. So I don't know, you're like manufacturing axles of a car, and they have to be within some certain tolerances in order to fit into the car. Now, when you actually try to manufacture this, you need to choose a point for which you're going to try to develop your product for. So I might choose that I want my radius of my axle to be, such and such. And this is my target for the parameters that I'm trying to choose. However, there's going to be some error, right? And if we assume that there's some Gaussian error around the tolerances that you have, then when I actually try to manufacture something with this set of parameters, I might end up with something here, or here, or here, or here, whatever. And if it's Gaussian, then you're going to have, this kind of circular error bound around what you're going to be able to produce. So when choosing what your target should be, you really want to choose your target to be as deep as possible inside of the set of admissible parameters, right? So that way, if your tolerances are off by a little bit, it's still acceptable. And so what we want to be able to find, really, is the Chebyshev center of a polyhedron. So we want to find the largest inscribed circle that I can fit inside of this polyhedron, and the point xc in the middle of that. Choose this as my manufacturing target. Does that setup make sense? I know I kind of try to go over it quickly. Okay, so want to find largest inscribed ball B in the polyhedron P, where my polyhedron is going to be in the same form that we've been writing. It's going to be the set of x's such that x satisfies all of our constraints. And my ball is going to be defined by its center and its radius. And it's going to be the set of, if I take my center point and I add some u to it, that u's norm must be less than or equal to r. So it's a set of all points where I take xc and add u to it, such that u is smaller or equal to my radius. So this does not look linear, right? Like if you see a ball, you should have alarm bells going off, being like, no, curvy things are not linear. But by doing some tricks, not necessarily the epigraph trick this time, we can try to reformulate this. So what we want to do is we want to find the maximum over our center and our radius, I'm going to find the ball with the maximum radius, subject to that ball must be inside of my polyhedron. So R here is affine, but this doesn't necessarily look affine. I don't really know what this means. So let's go ahead and figure that out. So this So what does it mean for the ball to be inside of the polyhedron? Well, the ball is defined by this xc plus u. So we need our xc plus u to be inside of the polyhedron for all possible u's that we choose, where u has to be less than or equal to r. Okay, this is starting to look a little more affine, but I still don't know what this p is, so let's go ahead and plug that in. What does it mean for a particular point to be inside of a polyhedron? Well, if some point x is inside the polyhedron, then it satisfies this. So that means that AI transpose, and we plug in this for x, xc plus u, must be less than or equal to bi. And this must be true, again, for all u. And all of my i's. So this looks pretty affine to me. We have, this affine function, and this is for a constraint, for I, 1 through m of these. But this must hold for every possible u that we come up with. I can't, write down every single possible u in this circle as my constraints in a computer program. So that's not going to work. So is there a way that we can turn this every single possible u into one u that satisfies the same constraint? This is what we're going to try to do. So first, it's useful when you're trying to do something with a variable to just get it alone. So I'm going to just move this over. Bi minus AI transpose xc, and then all those other things. So I have my u here. And this AI transpose u must be less than or equal to bi transpose AI, bi minus AI transpose x for every single possible value of u. So if I plug in any possible u that I have, such that its norm is less than or equal to r, then it should hold, that it's a lower bound on this. So can I find the maximum lower bound on this and replace this for all with just the u that satisfies the worst possible lower bound on this? Does this make sense? We want to satisfy this for all u. That means it must be able to be satisfied for the u that will maximize this side, subject to, so supremum over u, subject to so this must be less than or equal to bi minus AI transpose x c for all i's. You know what? I'll just do it over here. I'll leave that. So think for a second about how you might choose that u. Not too long, because we don't have too much time. So we have our AI transpose u. And we want to find the biggest one of this such that we have a norm of u. Well, when we have some inner product and we want to relate this to norms, a thing that should be ringing a bell in your brain are the words Cauchy and Schwartz. I don't remember how to spell this. Schwartz. Okay, so that's saying if I take these two vectors, that is going to be less than or equal to this. And the largest value of u that I could possibly get to maximize this is going to be r. So I'm going to replace this constraint with now moving this back over, I have AI transpose XC plus, and then this is going to be AI, the 2 norm of AI, R, plugging in for here. And then, what's the last term? Is less than or equal to BI for I equals 1 through M. So here we have an affine objective. Do we have an affine constraint? It's kind of weird, right? We still have this 2 norm in here. When you see a norm in the constraints, again, alarm bells should be going off because norms are not linear functions. However, what are our variables in this? Our variables are xc and r. Our 2 norm is not on xc or r. This 2 norm is on these AIs. So this is on some constant. So we could just replace, this with some constant that is equal to this. So I don't know, p, whatever. Because the 2 norm is not over our variables, it's not, it's still affine. So like, for example, y equals x. If I added y equals a squared times x, a squared is not a variable. A is not a variable. So this could just be equal to y equals bx, where b equals a squared. It's just a constant. Okay? So it's useful to have that alarm bell go off, but check if the things that don't look affine are over the terms that are variables or over terms that are constants. So in this particular case, we do have an affine constraint. So to recap, what we did is we took this constraint about some ball and some polyhedron. We then rewrote that to say, well, what does that actually mean based on what a ball and a polyhedron define? And we got this. And this was nice, except we had this have to be hold for all possible u. It's an uncountable number of u. So we asked, could we replace that u with a particular u that will maximize that lower bound? And that is how we were able to turn our Chebyshev center of a polyhedron into a linear program. So the set of admissible parameters would be like, the example I was giving of like you're designing some axle. The axle has to be between a certain lengths, between 2 different certain lengths, and it has to be within 2 different certain radii or something in order to fit inside of the car. So it would just be, what are your manufacturing constraints in this particular case? And if you end up, going for exactly the longest length that is still admissible, so like let's say you're right on this constraint here, if you end up producing an axle that is too long, it won't actually fit inside the car. So if you have some possible error around what you're trying to build, you want to make sure that your target then is as deep as possible into the set of admissible constraints. Exactly. So that way, if you end up aiming for this, and what comes out of the machine because of machine tolerance or whatever ends up being over here, that's still okay. So this error is fine. But if this error happened over here where you were aiming for this and you ended up with something out here, you have to throw away that part. And so that is why this is practically a useful example. Are there any other questions on the material that we covered today? Okay, in that case, I think we are 6 minutes early, so I'm happy to answer questions if you have any one-on-one. Thank you. squared n in the computational complexity, which at worst that would be the order, which is better than the order so the next ones are going to be talking about. And so it's because it kind of comes down to the trick that we talked about before, where it's always going around the vertex. And so instead of searching through the space of your domain, you're really searching through the vertex. And so the algorithms can be a little bit more efficient in how they transfer.
Okay.
And so it's nice